you too. Okay, so here we are working on our work, energy, and power practice problems. So I'm going to start with the very first one. I'm going to go to blue ink to begin with. Okay, the first one says that you have a person pulling a toboggan for a distance of 35 meters along the snow. So here's the toboggan, here's the rope. There's 94 newtons of tension in the rope. He moves at a distance of 35 meters. Makes an angle with the horizontal of 25 degrees. And they want to know what work is done. Work is equal to F cosine theta d. Now remember that this angle theta is the angle between F and D. So I only want the part of the force that's pulling the toboggan straight ahead. I'm going to call that Fx. And so the cosine of 25 degrees times the hypotenuse of 94 will give me Fx. And so when I did that, I think I got 81 point something. Let me stop for a minute and get a calculator. Okay, so when I multiplied those together, I got 85.19 newtons. So now I'm going to go over here and say, well, work is equal to 85.19 newtons. Cosine of the angle between F and D is now going to be the cosine of 0. And D is 35 meters. So if I punch that into my calculator, I'm going to get 281.75 joules. Okay. Part B says, what are you going to get if you just pull the toboggan straight ahead? So I'm going to say that the force is 94 newtons. It's going to act at an angle of 0 degrees. And it's going to act for a distance of 35 meters. So if I multiply 94 newtons times 35 meters, I get 3,290 joules. So that's the work done. Okay, number 2. Number 2 asks me, a person is refinishing an antique walnut table. In the process of sanding the tabletop, the sandpaper is rubbed back and forth 30 times. And each time it travels 0.6 meters. So it's going to travel a distance of 18 meters. And the question is, how much work is done by the frictional force? Work done by friction is the frictional force times the distance times the cosine of theta. The frictional force is mu, force normal. And this would be cosine of 180 because friction takes energy away. Mu is 0.85. Force normal is given to you as 1.5 newtons. And I do this for 18 meters of distance. So if I multiply, and the cosine of 180 is a negative 1. So the work done by friction should be a negative 22.95. And the negative just shows me that it's frictional force opposing the motion. Okay, number 3. Number 3 says the speed of a hockey puck decreases from 45 meters per second to a final speed of 44.67 meters per second. And it takes 16 meters to make this happen. And they want to know the coefficient of friction. So I said that KEI plus PEI minus the work done by friction is equal to KEF plus PEF. The potential energy never changes because the height never changes. So KEI minus KEF is equal to the work done by friction. So I have 1/2 mBI squared minus 1/2 mBF squared is equal to friction, which is mu mg, times the distance. That's my force of friction, that's my distance. Okay? So I have masses that can cancel out. So I have 1/2, 45 meters per second. Don't forget to square it. minus 1/2, 44.67 meters per second, don't forget to square it, is equal to mu times gravity of 9.8, and the distance is 16 meters. So when I did all that algebra, I got mu to be 0.094. Okay, number 4. Number 4 says that we have a sledgehammer, weight of 22 newtons, initial speed of 7.6 meters per second. Distance the stake moves into the ground is 0.025 meters. And they tell us that 40% of KEI is used to drive the stake into the ground. So I'm going to find my initial kinetic energy. 1/2 m is 22 over 9.8. VI is 7.6 meters per second squared. So the initial kinetic energy is, according to what I got, I didn't do that math, so let me stop it and I'll do it in color. So the initial kinetic energy is 64.83 joules. Now I want 40% of that. And that's going to equal the force that the stake exerts on the ground and the ground exerts on the stake times 0.025 meters, which is how far the stake went into the ground. And so when I did that, I got the force to be 1037.76 newtons. Okay. All right, number 5 says that you have a skier, goes up a lift 2,700 meters long. The lift is inclined at 15.6 degrees. And that's a 5 right there. And it wants to know what is the change in potential energy. Well, change in PE is mgh final minus mgh initial. Well, if he starts down here, there is no initial potential energy because there is no height above the ground. So delta PE is simply going to be mgh final. Well, I need to solve for h final. There's my h final. So I'm going to say the sine of 15.6 degrees times 2,700 meters will give me my h final. So the sine of 15.6 degrees times 2,700 gives me 726.1 meters. So now I'm going to take the mass of my skier, multiply it by gravity, and then multiply that by 726.1 meters. And I find that the potential energy of the skier has changed by 533,671.4 joules. All right, so let's go on to 6A. Pick a different color now. So 6A says that we have a very small metal ball, and it's going to come down the ramp, it's going to pop up, and then it's going to shoot up all the way to here. And I didn't label that point C, but I'm going to call that C. Here's B, and here's A. So conservation of energy, no friction. Conservation of energy tells me that the KE at A plus the PE at A equals the KE at B plus the PE at B, which equals the KE at C plus the PE at C. Now, I don't need all three of those points. So I'm going to use the ones that I think are easy. I'm going to use KE at A plus PE at A equals PE at C. Because I taught you a long time ago that gravity slows the object down to 0 at the highest point. So I have 1/2 mv naught squared plus mg height at A equals mg height at C. All my masses are present in every expression, so I'll get rid of that. So 1/2 v naught squared plus gravity times 3 meters equals 9.8 times 4 meters. And so I do all that algebra, and I solve for v naught, and when I did it, I think I got 4.43 meters per second. Yes, I certainly did. Okay, I'm going to stop this recording and then start another one. Actually, I think I can go a minute or two longer. Let's go on to 6b. Now in 6b you have swimming pool. No, I am going to stop it because we're going to run out of room. This is a longer problem.